Hello students, in this video we are going to discuss about the concept of relative maxima and minima. Okay, so firstly we'll try to understand that how do we check and what is the condition for the local or the relative maximum and minimum of the function. So to understand this particular concept, firstly we'll consider the case of a function of one variable. Let us suppose that a function y equal to f of x. Consider the function of one variable y equal to f of x, because we'll try to extend this particular concept for a function of multivariable also. So in this case, to understand this concept, suppose that this is our x-axis, this is our y-axis, and suppose that this is our curve like y equal to f of x, right? So in this case, if we just look at this particular curve, then we can realize here that this is the point where the function attained its maximum value, right? And this is the point where the function attained local minima. Local minima means if we compare its value with its neighborhood point, then this is the point where the function attained its minimum value in comparison to its neighborhood point. So this is the relative maximum, because if I compare its value with its neighborhood point, and this is the point where the function attained its maximum value. Similarly, this is also the point of relative maxima. This is also the point of relative minima. But how do we say that this is a point of relative maxima and relative minima? So basically, so firstly, we need to understand the concept of increasing and decreasing function. Firstly, we'll discuss about monotonic, increasing and decreasing function. Monotonic, firstly, we discuss about monotonically increasing function. Okay, so for that, so what is the monotonically increasing function? So again, this is our x-axis, this is our y-axis, this is our origin. And suppose I'm considering a function, say y equal to x. This is our function y equal to x. So in this case, you can see here, with the increase in the value of x, the value of function also increases. So we say that this function is a strictly increasing function. Okay, because if I say that this is somewhere here, we have a value x equal to 1. So corresponding value is y is also equal to 1. And say that this is our function, where the function, the value of x is 2, so this is the value of the function 2. So this is a point 1 1, and this is a point 2 2. So it means that with the increase in the value of x, the value of the function also increases. So we say that this function is a increasing function, strictly increasing function. Because what is the condition for increasing function? The condition is if x1 is greater than x2, then f of x1 is greater than f of x2. So this is the condition of monotonically or strictly increasing function, right? So this is how we can check that a function is increasing. But we'll try to discuss, because sometimes the function is given in very complicated form. In that case, it is difficult to identify that either your function is increasing or decreasing. So we'll try to identify some other condition also. So for that, what can we do? If I simply consider the neighborhood of a point, say f of x1 is greater than x2, means suppose x1 is x plus h and x2 is f of x, then f of x plus h is greater than f of x for some h greater than 0, right? So if this is greater than 0, so we can further write it as that f of x plus h minus f of x is greater than 0. Although h is greater than 0, if I divide it with h, then still this term is greater than 0. And if we consider that h is a very small number, say h tends to 0 from positive side only, then this is nothing but the condition of the derivative of the function. So what is the condition that a function is monotonically increasing at a point? So instead of x, I can consider point A also, that a plus h and a, right? So if we use this condition, then this is nothing but f dash a. So if f dash a is greater than 0, it means that function f of x is increasing in the neighborhood of a point A. Okay, so we can say that function is increasing function. So similarly, if we consider the condition for the monotonically decreasing function, monotonically decreasing function or strictly decreasing function. Then the condition is that suppose that this is our x-axis, this is our y-axis, this is the origin, and I can consider a function like this. So you can see here with the increase, because this side the value of x start increasing. So with the increase in the value of x, the value of the function start decreasing. Okay, suppose I can consider y equal to f of x, where f of x is say 1 upon x. So with the increase in the value of x, the value of the function start decreasing. So what is the condition for the monotonically decreasing function or decreasing function is strictly decreasing function is if x1 is greater than x2, then f of x1 is less than f of x2. This is the condition of strictly decreasing function. Strictly decreasing function. Okay, so in other way we can say that say x1 and x2 be the two neighborhood points. So we can say that f of x is greater than f of x minus h, where h is greater than 0. So automatically we can get an idea that x minus h is a point which is before the point x only. So in this case, if we find out the difference of these two, so f of x minus f of x minus h, this should be greater than 0, right? Okay, so we have considered the reverse condition. So f of x should be less than f of x minus h, because if x1 is less than x2, then f of x1 is greater than f of x2, right? So it means that this condition is it is less than 0, right? But because h is greater than 0, so if I divide it with h, then still the condition will remain same. And if we apply here the limit h tends to 0, then this is nothing but the condition of the derivative of the function. So what is the condition that if f dash x is less than 0, then we say that a function is monotonically, or you can say the function is decreasing function at that particular point. Okay. So this is the condition of increasing function and this is the condition of decreasing function also. Now what about the condition of the extreme point, right? What will happen if f dash x is equal to 0, right? F dash x is equal to 0 means when the tangent is the parallel to x-axis, means the slope of the function at that point is equal to 0. Suppose that this is the point A, then we can see here, okay, in the left neighborhood of a point your function is increasing, this side your function is increasing and this side your function is decreasing, right? But at this particular point your tangent is parallel to x-axis, because this side slope is increasing, this side slope is decreasing. Okay, so in this case at that particular point the slope of the function at that point is 0. So this is the condition of extreme point. Otherwise, if we remember the mean value theorem, which is a Rolle's theorem state that if your function f of x is continuous, continuous in the closed interval ab, right, and your function f of x is differentiable in open interval ab, and f of a is equal to f of b, then there must exist at least one point c which belongs to this interval where f dash c is equal to 0. Means that if there is a point, say this is the point I'm considering a1 and this is the point b1, where the value of the function at this particular point is same and the curve is continuous, means there is no breakage at all within this interval, and differentiable means the curve is a smooth curve, so there is no peak point, right? So in that case the curve is smooth, continuous, and the value of the function at the endpoints are same, and there must exist at least one point where the derivative of the function is 0, means that there must exist at least one point where the tangent is parallel to x-axis. So that point is called the extreme point. Okay, so it may be the curve is like this because at the end point the value of the function is same, but at this point the tangent is parallel to x-axis. So this is called the extreme point. This is the condition of the extreme point. So what is the condition of maxima? What is the condition of a maxima? So if we are saying that this is x-axis, this is y-axis, this is origin, so we are saying that if this is a point A, say A is a point of maxima, so A is a point of maxima if, so the condition is number one, that the derivative of the function at that point is 0. At the point A, the derivative of the function is 0. But in the left neighborhood of a point, your function is increasing function. And in the right neighborhood of a point, your function is decreasing function. So this side, your function is increasing. And this side, your function is decreasing. Okay, so it means that in the left neighborhood of a point, f dash a minus h, the derivative of the function is greater than 0, means your function is increasing function in the left neighborhood of a point. Number 3 is f dash a plus h is less than 0, means your function is a decreasing function in the right neighborhood of a point. Then we say that a is the point of maxima, or we can say that it is a point of local maxima because we are simply comparing its value with its neighborhood point, right? So this is the condition, but the problem is that again it is difficult to identify that this particular condition when sometimes we are given a very complicated function, right? To overcome this particular one, we'll try to identify for smooth conditions which we can easily check that either your function is a gives us the condition of maximum or minimum. So we have already discussed the condition of first order derivative. Now we are going to move to the second order derivative test. So what about f double dash a? So using the definition of first derivative of function, so this is limit h tends to 0, f dash a plus h minus f dash a upon h. Now, because a is the extreme point, so it means that f dash a is 0. So if we use this particular condition, then what will happen? So because f dash a is equal to 0, so it means that this is nothing but equal to limit h tends to 0, f dash a plus h upon h. So now we'll try to check what is the condition of maxima here. So the condition is in the left neighborhood of a point, it should be greater than 0, and in the right neighborhood of a point, it should be less than 0. This is the condition of maxima. So if h tends to 0 from negative, 0 from negative means if it is in the negative side, then a plus h is less than a. A plus h is less than a means we are considering the left neighborhood of a point. And it is already known to us that f dash a minus is greater than 0. F of a minus is greater than 0. And h tends to 0 from negative means h is also less than 0, right? So what does it mean? It means that limit h tends to 0 from negative f dash a plus h upon h. Now f dash a negative is positive, so your numerator is positive, but your denominator is a negative. This is positive, this is negative, and product of a into b is less than 0 if a is positive and b is negative, right? So it means that the product or the ratio is less than 0. So what does it mean that if we are considering the left neighborhood of a point, then its derivative is less than 0. Okay, right? Now this is the case if we are considering the left neighborhood of a point. What will happen if we consider the right neighborhood of a point? That means if h tends to 0 from positive, Then what about f of a plus h? Because h is positive, f of a plus h, f dash a plus h. It is already known that this is less than 0. Means f of f dash of a positive is negative. But h is already positive. So the ratio of f dash a plus on h, this is less than 0. Because this is positive, this is negative, and this is positive. Because this is negative and this is positive, so the ratio of negative and positive is negative only. So what do we conclude? That either s tends to 0 from negative or s tends to 0 from positive, the value of this derivative is always less than 0. So it concludes that a is a point of point of local maxima. What is the condition? The condition is f dash a is equal to 0 and f double dash a is less than 0. So this will gives us the condition of local maximum. Okay. So now we'll try to discuss about the condition of minima. What about the condition of minima? So again, I'm considering, suppose this is our x-axis, this is our y-axis, this is our origin, and now suppose I'm considering a curve like this. So here, say this is the point B. Okay, so you can see here in the left neighborhood of a point, your function is decreasing, and in the right neighborhood of a point, your function is increasing. So it moved from decreasing to increasing. If it move in this way, then we say that B is the point of minima. Okay, so what is the condition of minima? Number one, f dash b, because at this particular point the tangent is parallel to x-axis, so f dash b is equal to 0. Second one, in the left neighborhood of a point, f dash b minus h is less than 0, because it is a point condition of minima where h is greater than 0, right? And the third condition is f dash of b plus h, this is greater than 0. This is the condition of increasing function, and this is a condition of decreasing function. Okay, so again, so we'll try to apply the second order derivative test. So what about f double dash b? So using the definition of derivative, limit h tends to 0, f dash b plus h minus f dash b upon h, right? Basically, this is the formula of the derivative of a function f dash x. What is the formula of f dash x? F dash x is limit h tends to 0, f of x plus h minus f of x upon h. So we are simply taking the ratio of the neighborhood of a point, right? When the 2 points, they are very close to each other, and when we try to calculate the slope y2 minus y1 upon x2 minus x1, and the 2 points are very close to each other, and then the tangent line become, then the chord become tangent to the curve, right? So this is the definition of the derivative function. So we are simply extending it for second order derivative. So here, instead of function, we are considering first order derivative, right? Now here, because f dash b is 0, so we left with the condition that limit h tends to 0, f dash b plus h upon h. So now we are going to impose the condition limit h tends to 0 from negative, f dash b plus h upon h. Now because h tends to 0 from negative, so it means that your denominator is less than 0. But when h tends to 0 from negative means in the left neighborhood of a point, then f dash b plus h, because h tends to 0 from negative, so b plus h means less than b, because h is less than 0. So in the left neighborhood of a point, your function is decreasing. So it means that f dash b plus h is also less than 0. So the ratio of two negative number, like I write minus 2 upon minus 3, then its value is 2 by 3, which is positive, right? So the ratio of two negative number is positive, so it should be greater than 0. Okay, so this is the case of the left neighborhood of a point, means it is greater than 0. Now what about if limit h tends to 0 from positive? F dash b plus h upon h. Now, if h is positive, means h is greater than 0, then b plus h means greater than b. So it means that we have already discussed that your function is increasing. This is already positive. This is also positive. So the ratio of two positive number is also positive. So it means that in both the cases, what do we conclude that the second order derivative is always positive. So it will gives us the condition of a minima. So what is the condition of minima here? The condition of minima is f dash b is 0 and f double dash b is greater than 0. Then b is the point of minima. Okay, so if we conclude this thing, so how do we conclude that? That f of x uh, has a local maxima at the point x equal to a if f dash a is equal to 0 and f double dash a is less than 0, and f of x has local minima at a point x equal to b if f dash b is equal to 0 and f double dash b is greater than 0. Okay, but sometime what will happen, we have a point of inflection also, like we have a curve like which have a behavior like this. So firstly function is decreasing and then further decreasing, or we have a curve like this, your function is increasing and then increasing. So if the nature of the curve will not change, then we say that it is a point of neither maxima nor minima, right? So at this particular point also the tangent is parallel to x-axis, but this is a point of neither maxima nor minima, because in that case your function nature remains same. Okay, so in this case sometime your second order derivative is positive and negative, means in the left neighborhood of a point your function is increasing, right neighborhood of a point your function is also increasing. So it is negative or positive in the neighborhood of a point, so it is a point of neither maxima nor minima, right? Now we'll try to derive the same condition with the help of some other result. So what is the basic condition of a maxima and minima, right? So let me check here. This is the maxima curve and this is a minima curve. So we can say that this is the point of maxima. If I compare the value of the function at this point in its neighborhood point, then we find that this is the point where the function attains its maximum value. Means f of a is always greater than a plus h. Either h is positive or negative, right? So the value of the function at this particular point is always greater than its neighborhood point. And if this is the point of minima, see this is a point A and this is a point B. So B is the point of minima. This is the case of maxima, right? And B is the point of minima if f of B is less than f of B plus h for any value of h, either h is positive or negative, then this is the condition of minima, right? So to get this particular condition, what can we do? We can use here the Taylor's theorem. Okay, so Taylor series or Taylor theorem. So what is the Taylor's theorem? So because here we are assuming h to be a very small point, so otherwise the Taylor series is f of a plus h. So if the value of the function at a point is known, and the value of the function derivative of the function at the point is known, then we can find out the value of the function at the neighborhood of a point using Taylor theorem as f of a plus h time f dash a plus h square by 2 factorial f double dash a and so on. Basically, this is a Taylor series expansion of the function about the point a, right? So suppose that h to be a very small number, right? And I'm interested to find out the value of f of a plus h minus f of a. So what do we get here? This is h time f dash a plus h square by 2 factorial f double dash a and so on. So if h to be a very small number, then we can exclude the higher degree term, right? Then what do we happen? Suppose that I neglect all this term. So we have this term. So what do we get from here? If h is positive, because f dash a is the fixed value. F dash a is the fixed value. So if I consider h to be positive, then it has a sign. Say f dash a is equal to 3, right? It has a fixed value. So if I multiply with a positive number, it remains positive. If I multiply with a negative number, then it is a negative. So it means that with the help of this one, we are not able to get that either this is positive or negative. So it means that it is not possible to get the nature of the function at the point A, either this is a point of maximum or point of minimum. So what can we do? We simply ruled out this particular term. So because h is a very small number, so we are simply assuming f dash a is equal to 0. So the first condition is that f dash a should be equal to 0. So if f dash a is equal to 0, so what do we left with? It means that f of a plus h minus f of a, because h is a very small number. So now it is equal to h square by 2 factorial f double dash a, right? Now we know that the square of a number is always positive. Either h is positive or h is negative. This number is always positive, right? So it depends. Then the difference of these two terms, it only depend upon the value of f double dash e, because square of a number is always positive. 2 is also positive, so this term is always positive. So if f double dash a is positive, it implies that f of a plus h minus f of a is positive. So what does it mean? The value of the function at a point is less than the value of the function at the neighborhood of a point. So we can say that a is the point of minima, and we can say that a is the point of minima. And if f double dash a is negative, f of a plus h minus f of a, this is equal to h square by 2 factorial f double dash a. So if f double dash a is less than 0, it means that f of a plus h minus f of a is less than 0. Means a is the point of maximum, right? So this is the mathematical proof for the condition of maxima and minima also, right? Okay. So what do we conclude from here? If the second order derivative is positive, then we get a condition of minima, and if the second order derivative is less than 0, we can get the condition of maxima, right? Now we'll try to extend this condition for multivariable function. Now let us consider the case of function of two variable. Function of two variable. So function of two variable means now we are going to consider f of xy. So in this case, this is our x-axis, this is our y-axis, this is our z-axis, and this is our y-axis. So basically this time we are going to discuss about a surface, because now z is equal to f of xy. When we are considering any point here, so on the basis of that surface is generated. So this is say three-dimensional surface we are getting here. So we can say that this is the point of a maxima. So what will be the condition here? So in this case, if either I draw a tangent in the direction of in the plane parallel to xy plane, or we can consider this particular plane, right? That means this is the condition, means the partial derivative of the function with respect to x is equal to 0. This is the tangent line parallel to x-axis. So this is a tangent line parallel to y-axis. But this is a condition of partial derivative. So what will be the condition? That curly f upon curly x is equal to 0. This is the point, say AB. Then the partial derivative of the function at the point AB is 0. The partial derivative of the function at the point AB is equal to 0. That means the tangent is parallel to x-axis, parallel to y-axis, both of them are 0. So this is the condition of the extreme point or the stationary point, right? Now, what about the condition second order derivative? So in this case again, if because here it is a surface, so there are two things. One is if I take the projection of the surface in the xz plane, this is x-axis, this is the z-axis, right? So this is the origin. So in this case, what we see that in the left neighborhood of one unit function is increasing, then decreasing. So it means that the condition will remain same, that curly square f upon curly x square at the point AB, it should be less than 0. This is the condition of maxima. And even if I take the projection of the surface in the yz plane, taking this projection in this plane, again it is like this. In the left neighborhood of a point your function is increasing, right neighborhood of a point your function is decreasing. So we can say that curly square f upon curly y square at the point AB, it is also less than 0. Then this is a condition of maxima. So basically in this case, we need to check two derivatives with respect to x and with respect to y also, right? But what will happen? So there is some other condition also, that is the condition of a saddle. Okay, what is the condition of a saddle? Because sometime we are having a surface like, sometime we have a surface like, okay, so we have a surface like this. Then what will happen? So we have a surface in this way. So if I take its projection in the xy plane, this is x-axis, this is y-axis, and this is z-axis. So when I'm going to take the projection of the surface in the xz plane, this is x-axis and this is z-axis, then it look like this one. Look like this one means that this is the point of minima. This is the point of minima. But if I take its projection in the, if I take its projection in this way, like if you just look at this particular part, then this is a condition of maximum. Like this is y-axis, this is z-axis. Then at this particular point, its nature is like this in this particular side, right? Its nature is like this. So it is a increasing at that. This is a point of maxima in a yz plane, but this is a point of minima in xz plane. Then this point is called a saddle point, where curly square f upon curly x square is less than 0. That means it is a condition of, sorry, greater than 0 means it is a condition of minima, and curly square f upon curly y square at the point AB is less than 0, is at the point AB is less than 0. So it is the condition of maxima on one side and minima on other side. Then that point is called a saddle point because it has a shape like a saddle. A shape like a saddle. Okay. So what do we conclude from here? So in case of two variable function, so if your function depend upon two variables, then the condition is we find out first order derivative at all the points, and then we check and we put its derivative equal to 0. It will give us a point x and y equal to AB, means the derivative of the function at the point AB is 0. And second one is if the second order derivative at the point AB is less than 0 and second order derivative at the point AB is also less than 0, then we can say that AB is the point of maxima. And if curly square f upon curly x square at the point AB, curly square f upon curly y square at the point AB is greater than 0, then AB is the point of minimum, right? And if they are of alternate sign, if curly square f upon curly x square at the point AB into curly square f upon curly y square at the point AB is less than 0, means curly square f upon curly x square and curly square f upon curly y square are of opposite sign, then it is the saddle point. It is a saddle point, means it is the point of neither maxima nor minimum, right? But because when we are having two variables, then there is one more derivative, curly square f upon curly x curly y. This derivative also play an important role. So to get the role about this particular derivative, so we'll try to understand the role with the help of a mathematical derivation, right? So what can we do? Again, we come to the Taylor series expansion, but now this time we are considering the Taylor series expansion for two variables. So suppose we are considering f of a plus h, b plus k minus f of ab, right? Because what is the condition of maximum and minima otherwise? If the value of the function at the neighborhood point is greater than the value of the function at the point, then this is the condition of minima, right? Means I can consider this particular function. This is the point AB. So if I consider this point or this point or this side or that side, so everywhere the value of the function is greater than this particular point. So this is the condition of minimum. And if the value of the function at that point is always greater than the value the neighborhood point, then this is the condition of maximum. So we'll try to check the nature of the function at the neighborhood of point, the difference, right? So consider the Taylor's theorem for two variables. So Taylor series expansion for two variable function. So what is the expansion here? F of a plus h b plus k. So this is equal to f of ab plus. So we are simply considering it as h time curly f upon curly x at the point AB plus k time curly f upon curly y at the point AB. So this is for first order derivative. For second order derivative, 1 upon 2 factorial h square curly square f upon curly x square plus 2hk curly square f upon curly x curly y at the point AB plus k square time curly square f upon curly y square at the point AB, and so on. So for first order derivative we have a 2 term, for second order derivative we have a 3 term, for third order derivative we have a 4 term, third order derivative with respect to x, 2 order derivative with respect to x, and 1 order with respect to y, then 2 order with respect to y, 1 order with respect to x, then third order with respect to y, and so on, right? So we'll simply try to see that what is the nature of this difference. Okay, so if I'm assuming h and k to be a very small number, then we are neglecting the higher term, right, in the same way, because I'm saying that h and k, they are very close, they are very small number. So I'm saying that this is equal to h time curly f upon curly x at the point AB plus k time curly f upon curly y at the point AB, and neglecting the whole or higher term, right? Neglecting higher power term. So I'm simply considering this one. Now what will happen? Now again, they are fixed value. They having fixed value. So if I take h to be, suppose k is 0. Suppose I consider k is equal to 0. So in this case, if h is positive or h is negative, so according to that, we have a different sign. Sometimes it is positive, sometimes it is negative. Same is for if I put h equal to 0, then k can be positive, k can be negative. So it means that we are not able to conclude anything, right? So if h is positive or h is negative, the difference may be positive or negative. So it means that we are not able to conclude anything. So what can we do? So we simply neglect this term. We simply reject this term. Okay, so how do we reject this? We are assuming curly f upon curly x at the point AB is 0 and curly f upon curly y at the point AB is 0. So if these two terms are 0, it means that this term is 0. This term is 0. So it means that now, because h and k are small, so we are saying that it is equal to second term, right? Then what will happen? So f of a plus h, b plus k. Now this is minus f of ab. Now this is equal to 1 upon 2 factorial time h square curly square f upon curly x square at the point ab plus 2hk curly square f upon curly x curly y at the point ab plus k square curly square f upon curly y square at the point ab, right? Now, so first step is we are going to use some general notation because it is very tedious job to write in this way. So let r is equal to curly square f upon curly x square at the point AB. S is curly square f upon curly x curly y at the point AB. And T is curly square f upon curly y square at the point AB. Right? Because basically I want to know that either this term is positive or negative, right? So for that particular purpose, now what will happen? F of a plus h b plus k minus f of ab. This is equal to 1 upon 2 factorial time. This is h square time r 2hk time s plus k square time r. Now we know one thing that the square of a number is always positive. Basically, how can we define a positive number or negative number? So positive number is defined as if it is equal to the square of a number, then it is always positive. And negative number is defined that if I multiply a positive number with negative sign, then it is always negative. This is negative number. This is always positive, right? So what I try to do, I try to convert it into perfect square form. So I have a two option. Either I can multiply the entire expression with r, or I can multiply the entire expression with sorry, or I can multiply the entire expression with t because k square t square is positive or h square r square is positive, right? So if I say multiply and divide by r, then what will happen? This is h square r square 2h r k s plus k square t r. Now, now if you just look at here, this is a square, this is 2ab, and now what term is missing here? B square. So if I add and subtract b square, then what do we have? 1 upon 2r h r square plus 2 times h r k s plus k s whole square. K s whole square, or I can write k square r t minus k square is there s square, right? Now this is equal to 1 upon 2r. Now this is a perfect square hr plus ks whole square, and this is k square time RT minus S square. Now the square of a number is always positive, right? This number is also positive. Now, if this number is positive, if this number is also positive, then we can say that the entire expression is positive. So what is the condition? If RT minus S square is greater than 0, that means this whole term is greater than 0. So it means that the sign of this particular part only depend upon R. Okay. So if R is greater than 0, means f of a plus h b plus k minus f of ab is greater than 0. And what does it imply? It implies that ab is a point of minima. AB is a point of minimum. And what is R? R is a second order derivative. Okay, it means second order derivative is greater than 0. So second order derivative greater than 0, it already gives us the condition of a minimum, right? So it is the same thing. So basically we have imposed one additional condition that RT minus S square should be positive, right? And if RT minus S square is less than 0 and R is less than 0, it implies, sorry, greater than 0 and R is less than 0, it means f of a plus h b plus k minus f of ab is less than 0, right? Because this term is already positive. If R is less than 0 means this difference is less than 0. It means that AB is the point of maxima. Okay, the same kind of condition we can get if we multiply it with T also, right? For example, I'll show you. If I multiply it with T, then we can get here 1 upon 2T. This will be h square RT 2h s kt plus k square T square, right? So k square T square kt 2hs. I need to simply add and subtract h square s square, right? So h square RT minus s square, and here h square s square plus 2hs kt plus k square t square. Then this is equal to 1 upon 2t. So this is h square time RT minus s square plus hs plus kt whole square. Now again this is positive, this is positive. If this is positive, then the value only depend upon t. So if t is positive, then it is a point of minima. If t is negative, it is a point of maxima. So it means that what do we basically conclude? Now the conclusion is f of xy is a function. Then the first step is we find out first order derivative at the point AB and put it equal to, sorry, we firstly find out first order derivative, put it equal to 0. Then the value of x and y, whatever the value we get here, we name it as a point AB. And then we calculate second order derivative with respect to x at the point AB. We name it as R. We calculate second order derivative at the point with respect to y at the point AB. We name it as t. And we calculate second order derivative with respect to x and y at the point AB. And we name it as s. And then we calculate RT minus s square. Now we have already discussed here if R and T are of opposite sign. That means if their product is negative, if they are of opposite sign, means RT is negative. If R into T is negative, S square is already positive, so minus means is also negative. So RT minus S square is always negative. So it is a point of neither maxima nor minima. Okay, if RT minus S square is less than 0, it is a point of neither maxima nor minima. But if it is positive, then we have a two condition. R is positive, T is positive, then we say that this is the condition of minima. and RT minus S square is greater than 0, but R is less than 0 and T is less than 0, then this is a condition of relative maxima. So this is the condition for the relative maxima and minima for the function of two variables, right? So we also have a condition for the three variables also, but we'll try to discuss that particular part with the problems of the function of, okay, let me try to discuss that particular one also. So what about if we have a function of three variables? So to get the extension of three variable function, so what can we do? Let us try to rewrite this condition in other way. So what is the condition we have discussed for two variable? If f of xy is a function, we find out first order derivative with respect to all the variables x, put it equal to 0. We calculate its derivative with respect to y, we put it equal to 0. So we get two conditions, and after solving these two conditions, we get the value of x, y, say that is the point AB. The second condition, we calculate second order derivative with respect to x at the point AB, with respect to y at the point AB, and with respect to xy at the point AB. And then we construct one matrix A with element as, I'm assuming x as our first variable and y as our second variable. So how do we construct a matrix? The first one is A11. So fxx is partial derivative with respect to x, fxy partial derivative with respect to xy, fyx partial derivative with respect to xy or yx, they are same because we are assuming that the partial derivatives are continuous, and fyy, it is same like we are considering a matrix A11, A12, A21, A22. So we are assuming 1 as our first variable and 2 as our second variable. And instead of the value, we are simply considering the derivative of the function at the point, right? And what is the condition of maxima and minima, right? The condition is if fxx and fyy, they are positive, means the principal diagonal elements are positive, principal diagonal elements are positive, and the principal minors are positive, principal minor. So what are the principal minors? fxx and fxx fyy minus f of xy whole square, means the determinant of a. If it is positive, then AB is the point of minima, is the point of minima, right? And if f of xx and f of yy is less than 0, of course we are calculating the value at the point AB. We are calculating second order derivative at the point AB only. So if they are negative and principal minors are of opposite sign, principal minors are f of xx less than 0, then f of xx, f of yy minus f of xy at the point AB square is greater than 0. So negative, positive, alternate sign. Then AB is the point of maximum. Okay, this is the same condition which we have already discussed because this is R, and this is T. This is R and T, and this is RT minus S square. RT minus S square is positive and R and T they are positive, then this is a condition of minima. And if R and T they are negative and RT minus S square is positive, then this is a condition of maximum. Okay. So now we are going to extend this condition for three variables, right? Then what is the condition for three variable function? So we suppose that our function depend upon three variable f of x, y, z. And firstly we find out first order derivative with respect to x, first order derivative with respect to y, first order derivative with respect to z, and put them equal to 0. So after solving this system, we will get the value of x, y, z. So this is say this is equal to point A, B, C. Then we find out second order derivative with respect to x, with respect to y, with respect to z, with respect to x, y, which is same as with respect to yx, with respect to xz, which is same as with respect to zx, with respect to yz, is same as with respect to z, right? And then we construct a matrix A. And this time we have a three variables, so we are going to construct a 3 cross 3 matrix. What kind of matrix? A11, A12, A13, A21, A22, A23, A31, A32, A33, right? So our first variable is x, second variable is y, third variable is z. So f A11 means fxx, A12 is fxy, A13 is fxz, A21 fyx, A22 fyy, A23 fyz, A31 fzx, A32 fzy, A33 fzz. Now, what is the condition of maxima and minima? So, if all the principal diagonal elements are of same sign, means either positive or negative. Say, if f of xx is positive, f of yy is positive, f of zz is positive, and the principal minors are also positive, means f of xx is positive, first one, this one, f of xx, f of xy, f of yx, f of yy is positive, and the whole determinant of is positive. Then ABC is the point of minimum. And what about the condition of maxima? And if f of xx means all the principal diagonal elements are negative, and the principal minors are of alternate sign. Alternate means first one is negative, second one is positive, and third one is again negative. Negative, positive, negative. Then ABC is the point of maximum. Maxima. And if they are not of same sign, then it is a point of neither maxima nor minimum, right? If they are of not same sign, that is a point of neither maxima nor minimum. Okay, so this is the condition of maxima and minima for three variables. I hope you understand the concept of this particular part, that what is the concept of relative maxima and minima for one variable, for two variable, or three variable functions. Okay, in the next video we'll try to discuss some problem based on the function of two variables and more variables, and we'll try to consider some problems. Okay, thank you and have a nice day.